Hello, physics. Welcome to another flipped lecture. We're going to be beginning chapter 19 today. And for all of those of you who were really sad because chapter 18 didn't have enough math in it, I'm going to fix you. You're going to be thrilled today. Chapter 19 has plenty of math, so don't worry about that. I've got what you need, and it's going to be wonderful. We're giving you the underlying understanding that you're going to need in order to be able to analyze circuits. And we're going to start looking at circuit components next week, and slowly over the course of the next couple of weeks, going to be adding several circuit components to your life, and we're going to spend the next probably month or so in circuits. So we're going to get you the fundamental understanding today to be able to jump into that. So the first idea is the concept of an electric field in general. What is an electric field? Well, when you have a source of charge, positive or negative, it influences its environment in a predictable way. And it influences its environment close to the source of charge, and not as strong further from the source of charge. And so there is a model called the electric field model that helps us understand how a source of charge interacts with its environment. Now, the things that we're going to show you are a model. So these don't actually exist. There are not, in truth, lines going from a source of positive charge to a source of negative charge, but everything behaves as if there were. So it's a model, and remember from the very first lecture, models are ways of interpreting and explaining and predicting data that do not necessarily themselves have a perfect correlation to reality. So, having restated that, the field model is that we're going to pretend that from a source of positive charge, there are these things called lines of force that go from the positive charge out in all directions. They radiate outward in all directions from a source of positive charge, and they can be curved so that they all end at a source of negative charge. Okay, so in the little picture that I have here, this is a source of positive charge, and it's brought near to a source of negative charge. And lines of force originate from this source of charge and go out in all directions. But then they curve so that they end at the source of negative charge. So even this one that goes off the map, it curves all around, then comes back in over here and ends at the source of negative charge. And this one goes this way, curves off the map, and comes back to end this way at the source of negative charge. So directly between them there are nearly straight lines, but they always leave radially from a source of positive charge, and they end radially at a source of negative charge. The further you pull these two apart, the more lines you'll see bending here to make that pathway happen. And if they're so far apart that they can't sense each other, then those lines are going to jump to some other source of negative charge and end there. So field lines always start at positive, end at negative, and they're curvy, okay? And they leave radially in all directions from a source of positive charge. The field strength can be implied by the number of lines that are drawn per unit area. So right here, if you were to take, like a square centimeter of this drawing, right here, there's a lot of lines of force. And so the field strength is pretty strong right there. But if you take the same square centimeter out here, no lines of force in this particular drawing. So the field will be very weak right there. And so the closer you get, the more lines of force you encounter per unit area, the stronger the field is. So that's just a way of predicting field strength, okay? And again, these don't actually exist, but there are ways of helping us understand how fields work. The arrows are drawn the path that a hypothetical test charge would take if it were massless and if it had a positive charge. So massless means that it's not going to push back. The gravitational effects don't come into play. But it does have a positive charge, so it's going to be repelled by this guy and go zipping along this line and land at the negative one. If you release it right in the middle, it's going to go straight across. If you release it right here, it's going to curve way out before it comes back. And that's the path that these things would actually take. So these lines of force, while not truly existing, they do describe and predict and explain observable data. Okay, so that's a field model. So how strong are these electric fields? One way of figuring that out is to use an equation that takes the strength of the charge into account and your test charge's distance, or the point where you're measuring the field's distance from the source of charge, and then Coulomb's constant, which we found out last chapter, and does a little math that looks a lot like gravity. And you're going to see several equations here that remind you of gravity math, and that's because it works very similarly. The gravitational force and the electromagnetic force are both fundamental forces of nature. And as God was designing the universe, you know, one design for a particular force is used very similarly for another force. So their math looks a lot like each other. Okay, so E, we're going to use capital E as the strength of an electromagnetic field, and little k is the same thing that it was before. Little k is Coulomb's constant. Capital Q is the source of the charge. We've used that pretty consistently for a while now. And then R, you can understand as the radius of separation. So how far apart are they? So the point that you're measuring the field, or the point where your hypothetical test charge exists, how far away is that from the source of charge? How much charge is there? Using that, we can calculate the strength of the field. So R squared is the square of the radius of separation. This is Coulomb's constant. This is the strength of the charge. Multiply and then divide, and you get the strength of the field. The strength of the field is measured in newtons per coulomb. Coulomb, remember, is the unit of charge intensity. How much charge is there? And Newton is force. So it's saying that for a given amount of coulombs, it's pushing with a certain amount of force on your test charge, or on the measuring device that's measuring the strength of the electromagnetic field there. Okay, so it's measured in newtons per coulomb. We also have to make sure that we're watching our signs. These are all vector measurements. So if my test charge is sitting here at some radius away from the source of charge, I'm measuring this vector E, right? The vector coming out of the source of charge and whacking my particle. And this vector always points away from a source of positive charge. So if I happen to have a source of negative charge here, then I would need to make sure that my vector is drawn pointing at the negative charge. If this is a positive charge, then I have to make sure that my vector is drawn pointing away from the positive charge. The magnitude will be the same. The magnitude is not influenced by the sign, but the sign of Q will determine the sign of E, and we have to make sure that the vector always goes away. So if this is positive, then E is positive, and E is going away from the source of charge. If this is negative, then E is negative, and it's always going, and then it's going towards the source of charge. So just watch your sign. Okay? So let's do an example. If we have a hypothetical field of 2.00 coulombs, sorry, a charge, hypothetical charge of 2.00 coulombs. This is a massive charge. Coulombs are big. So this is a lot of static electricity, a lot of electric potential right there. And I am only 3.8 meters away from that with my test charge or with my measuring device. And I want to know what's the force of the field on my test charge or on my measuring device. So again, here's my test charge, my point charge that has a charge of 2.00 coulombs, and I am 3.80 meters away. So E is what I'm finding. K is my Coulomb's constant, 8.99 times 10 to the 9th. And remember, K is pretty easy to remember if you just think of 9. 8.99 is really close to 9K, and 10 to the 9th. Times 2.00 coulombs, so that's Q. This is positive. I didn't specify that it was positive or negative. If there's not a sign, it's positive, right? So plus 2.00 coulombs. And then I'm going to divide that by my radius of separation of 3.8 meters. I'm going to square that. So let's square that. 3.8 squared is 14.44 meters squared. And then 8.99 times 10 to the ninth times 2 is 1.798 times 10 to the 10th. When I divide, I get 1.24515, and it kept going, times 10 to the ninth newtons per coulomb. But this is too many significant digits. I only have 3. I need 3 significant digits. 1.25 times 10 to the ninth newtons per coulomb. So that means that for every coulomb of charge, I'm experiencing 10 to the ninth newtons. 10 to the ninth newtons is a stupidly large force, right? And so your test charge would go zipping away very quickly from that radius of separation from that large of a charge. Okay, that's how you do that equation. Let me know if you have any questions in the comments field below, or tomorrow when I see you in class. Let's keep going. You saw this crazy picture at the beginning and you thought, what is that man doing with a floating candelabra? Well, you'll understand everything involved about this picture actually in 2 weeks, 3 weeks, when we get more into the magnetic aspect of the electromagnetic force. But for now, take a look at this picture and I'll help you understand part of what you're seeing. This is a very large electromagnetic field emitter. This is creating a huge electric charge right now. All right, so this field is coming out of here, and remember it's radiating in all directions. So the field is coming out and in and up and down and in all directions. And the electromagnetic field is so strong that the light bulbs on this candelabra don't even have to be plugged in by a wire. They are receiving electromagnetic radiation at such a large magnitude that the light bulbs are all glowing. The light bulbs are on, even though there is in fact no wire going there. And then the other part of that is that this plate is responding magnetically to the electromagnetic field here. This plate is not a magnet, it's just a piece of aluminum, but it is being repelled by the electromagnetic force, by the electric field coming off of here, so much that the weight of the candelabra and the weight of the plate are being pushed up. Remember, the force of an electric field is newtons per coulomb. So it's experiencing real newtons, and it is flying, it is levitating because of the strength of the field. And the strength of the field is also enough not only to lift the plate, but to light the bulb. So it's a real thing. An electromagnetic field is a real thing, and it can do real work. And here it's doing work by lifting this plate and lighting the bulbs. So, and this guy obviously thrilled by what he's seeing. We'll explain the magnetic aspects of that in a little while. And since electromagnetic fields can do real work, they represent the potential for work, even if no work is being done by them at the moment. So there is such a thing as the electric potential energy of a field. How much work can that field do? And if you remember, kinetic energy and mechanical energy and potential energy, these are all terms that get used together in a lot of equations. So a field can push things away or draw things to itself depending on its charge, right? And the moving of things by the field is kinetic energy. And so the field represents potential energy, even if nothing is being moved. So what is the strength of the potential energy of an electromagnetic field or an electric field, just based on how far a test charge is away from the field and the strength of the field? So you saw an equation that looks like this already, only this was big E for the strength of the field, and there was no little q. Now if we add little q, all that we're doing is we're saying now there's a charge from the test charge. So when we add the test charges charge into the picture, we're no longer looking at just the strength of the field, but we're looking at what can potentially be done, what's the work potential for that particular test charge in the strength of the field. Okay, so it looks a lot like gravity. Here we have two quantities that are of the same unit being multiplied together, divided by the square of the radius of their separation, and times a constant. Look at gravity. Remember gravity from several chapters back? We have two quantities, the masses of two objects in the same unit, being multiplied together, divided by the square of the radius of their separation times a constant. It's the same kind of equation. It's just that this one is looking for the potential energy of an electric field, and this one is looking for the force of gravity. But it's the same math. And again, they're designed by the same mind. The electromagnetic force and the gravitational force both came out of the mind of God. So of course, we would expect a common designer to use a common design. Just like GMC puts out Chevy trucks and puts out other brands, and if you look at how these parts of the different vehicles are put together, it's just slight changes. It's the same design, and the same can be said here for the electromagnetic and the gravitational force. Same math, slight differences, and we see that designers do that a lot. Okay, so this is the potential energy of a magnetic, sorry, I keep saying magnetic, of an electric field, of an electromagnetic field in the electrical aspect of it, okay? We can look at this another way. We can look at the potential that that can be done at any point in the field. So here, we're no longer looking at the test charge, we're just picking a location. Here's the strength of the field, here's how far I am from the source of the strength of that field. And I'm going to say, what work can I do here? And when we do that, we talk about something called voltage. Voltage is the work potential because of a particular electromagnetic field and how far I am away from the source of that charge. Strength of the field and my distance from it. The exact same, again, idea, we could look very similarly at gravity. We could say little g, the acceleration of gravity, right? How far could I fall given this strength of gravity? And we could come up with a similar concept for the potential of gravitational work that could be done at that distance from the ground. So again, it's very similar, and we use the term volt to describe this, right? A volt is measured as the strength of an electric field and my distance from that strength. And just let's compare, again, gravity and electrostatics. So the force of an electric field is Coulomb's constant times the two charges divided by the square of the radius of their separation. The force of gravity is the gravitational constant times their masses divided by the square of the radius of their separation. So same kind of math. Field strength, I didn't give you this formula, but just to compare, is the force of the field divided by the charge. And similar idea, the force of gravity divided by the mass could give you the acceleration of gravity. Field strength, I didn't give you this exact same arrangement, but again, field strength, Coulomb's constant, the charge that I'm dealing with in the radius of the separation squared, same idea, gravitational constant, mass of an object, radius of its separation, can give you little g. Even the numbers look similar except for the power of the exponent. Here we have 8.99 times 10 to the 9th. Here we have 6.667 times 10 to the negative 11th. So you can see, the numbers are of similar magnitudes on either side of 0. We talk about a charge unit as a coulomb and the mass unit as a kilogram, but the math is eerily similar between these two forces. And again, that's just evidence that the same designer designed both forces. Okay, electric potential difference, the volt. So let's look at the volt here. If you want to know what is the voltage at a particular point in a field, you can do the math, and I showed you that on the last slide. But more often than not, what you want to know is the voltage difference between 2 points. Usually 2 points in a circuit, but it doesn't have to be. It can be 2 points in an electric field as well. And voltage difference is what machines use to do electrical work, to do mechanical work with electrical energy. And so they don't necessarily care about the absolute value of the magnitude of the field strength somewhere. They want to know, if I put one end of my wire here and one end of my wire here, what's the difference and what work can I do because of the difference in volt, in charge, the difference in charge there. So we talk about charge separation or voltage separation or voltage difference. And what we're talking about is 2 points in a field or 2 points in two different fields. It doesn't really matter. What's the voltage at one point? What's the voltage at the other? What's my change in voltage? What's my difference in voltage? And this voltage difference or voltage separation is going to be useful for all kinds of things, because if I have a voltage separation, I can create current between those two places. I can spin a motor. I can light a bulb, things like that. Okay? We measure those in this unit called a volt. A volt is a derived unit of joules per coulomb, amount of work that I can do per unit charge. Okay? And we call a J over C a joule per volt, a joule per coulomb, we call that a volt. We don't necessarily need to know the absolute field strengths to work in delta V, to work in differences of volts. We just need to know what's the voltage here, what's the voltage here, what's the distance of their separation of charge, what work can I do because of that. So delta V is something that we use a lot. And this little graphic down here, voltage is like pressure in a wire. We're going to get into circuits later, but for right now, just start thinking about voltage as pressure. It wants to move electrons from a high voltage to a low voltage. The voltage separation makes electrons want to go somewhere. And when electrons get to go somewhere, we have current, and we can do work because of the current flowing. Okay, we'll get to current particularly later. Just I want to start loading your brain with concepts that will help you in a couple of chapters. So voltage, think of as pressure. Pressure that wants to move electrons. Alrighty. The last concept that we're going to cover today is kind of different from the others. We've been talking about fields, and we've been talking about voltage and charge separation. Now imagine that there is a series of points in a field where the voltage is identical across all of those points. It has the same force from the field. It has the same work potential as all the points, common to it in the field. So you have a point of charge and energy coming out of it in all directions. And I could find some shape in that field where all the points in that shape have the same voltage potential. They can do the same amount of work at that point as the other points that I've identified. So here we come up with a concept called a surface, and it's been a while, seniors, since most of you took geometry as sophomores. So let me remind you, the word surface in geometry does not mean like an item where this is a surface. A surface in geometry is some connected series of points in three-dimensional space. It could be a flat thing like this, or it could be round, or it could be any kind of crazy shape, right? But it's a connected series of points in three-dimensional space that share some attribute. In this case, we're talking about points in three-dimensional space that share the same electric potential. So we call these equipotential surfaces. Equi meaning the same, potential because they have the same electric potential. They have the same voltage across all of these points in space. So I just gave you some examples of what it might look like. If I had a point of charge or a charge that was concentrated in a rod, then I would find that there's a cylinder around that rod that would be an equipotential surface. All the points on this cylinder would have the same, would experience the same field force, would have the same voltage, things of that nature. Okay? Or different shaped objects would present different equipotential surfaces. But a surface is just some series of points are in space where I could identify that everything there has the same voltage, has the same potential charge. Okay? That's it. Let me know if you have any questions. We will talk about this all week. God bless you. Have a wonderful night.